This video is going to go through 4 different examples. Watch what you need to. First step here is write down my balanced chemical equation. What I know, my question mark, and my conversion factors. What I know here is grams. In order to get grams from moles, grams to moles, I'm going to use molar mass, which I've written down as my conversion factor. Here, what I'm looking for is my volume of a gas. And because it's at SATP, I can use my molar volume, which is 24.8 liters per mole. My first step is I'm going to find my moles of my known. I will first do it using proportions, then I will do unit analysis. So I know that I have 300 grams, and I am going to set that up equal to 44.11 grams in 1 mole. So how many grams do I have in X moles? My answer there is I get 6.80 moles of C3H8, which is propane. Again, I'm not clearing my calculator because I want to keep all my decimals. My second step is I need to find the moles of my unknown, which means I'm using my molar ratio. So I need to put my moles of propane on the bottom, so C3H8. I need to put my moles of oxygen on the top, so moles of O2. I'm going to have 5 moles of O2 for every 1 mole of C3H8. What I'm doing here is I'm taking my moles of propane, and my moles of propane are disappearing. And for my answer here, I am going to get 6.80 multiplied by 5. Again, I'm not clearing my calculator. I have 34.0 moles of O2, and I'm still not clearing my calculator. What I need to find at the end is I need to get into liters of O2. And in order to do that, I am going to multiply it by my molar volume. And my molar volume, I have 24.8 liters in every 1 mole. So I'm taking my 24.8 and multiplying it by my 34, and I am going to get 843 liters of oxygen. Doing unit analysis, I have my 300 grams of C3H8 multiplied by my molar mass, which means now I have moles of C3H8. In order to get rid of my C3H8, I have my moles on the bottom. This is my mole ratio. Then my C3H8, I'm multiplying it by 5 moles of oxygen. Again, my mole ratio. My moles and my moles cancel out, and my final answer will be 843 liters of O2, just like it was at the top. So this question, you'll notice that it is a volume of ammonia, and our reaction here shows that we have all 3 gases, which means that if it's at STP or SATP, we could use our molar volume. But if it's not at STP and SATP, you have to use the ideal gas law. So on the left-hand side, hydrogen, it's given me grams, which means I can use my molar mass in order to get it into moles. But my conversion on the right-hand side, because it's not STP or SATP, I have to use my PERV-NERT. So my first step here is finding the moles of what I know, which means I am using my molar mass, which is 2.02 grams in 1 mole, to figure out my moles of hydrogen. In this, my grams and my grams are going to cancel out, and I can immediately use my mole ratio, and that means I'm going to have to put my 3 moles of hydrogen on the bottom and my 2 moles of ammonia on the top. If you look at canceling out, my moles and my moles will cancel out, my hydrogen and my hydrogen will cancel out, which means now I have 2 moles of ammonia left over. My answer here will be 2,475, and again, I'm not rounding, moles of ammonia. Now that I have my moles of ammonia, I can go back and use my ideal gas law, which is PV equals nRT. The question gave me the pressure. I'm looking for my volume. The moles I just calculated are we always have, and the question gave me my temperature, which means I have to rearrange this equation for V. So I'm going to have V is going to equal nRT over P. Now I have to plug in all my variables. So I have here my moles, which is 2,475. I just calculated that. 8.314 is my R, and I'm using my kPa because my pressure was in kPa. And then 253 is my temperature in Kelvin. We're always using Kelvin all the time when we're dealing with gases. So again, I'm not rounding my calculator, but I'm doing 2,475 plus all the decimals multiplied by 8.314 and multiplied by 353 divided by 450. And I'm going to get a final answer of 16,143 liters. Because I was given 7.5 in my answer, I have to have two significant digits. So what I'm going to do is I'm going to divide this by 1,000 and say that this is the same as 16 kiloliters. And now I have my two significant digits. This is solution stoichiometry. So we are asking for a volume. In order to get moles from volume here, it gave us the concentration. And we are given a volume, and in order to get to moles from that volume, we are able to use the concentration as well. So in this example, both conversion factors are concentrations. My first step here is find the moles of what I know. So I'm finding the moles that I know in two different ways. In the top version, I'm going to do 1 times 12.9, and I'm going to get my answer of X is going to equal 12.9 kilomoles, and that's because I didn't get rid of this kilo that I have up here. In the bottom example, I'm going to be able to say that I'm going to cross out the liters, but I can't cross out the kilo. So again, in this point, I'm going to have kilomoles. In order to find moles of what I don't know, I'm going to use my mole ratio. Up here, I have my kilomoles of H3PO4, which means I need to put my 1 mole of H3PO4 on the bottom and my 2 moles of ammonia on the top. In my unit analysis on the bottom, I can do the same thing. Now I have my moles and my moles of H3PO4. H3PO4 cancel out, so now I have my moles of ammonia as my answer on the bottom. On the top, I'm going to get my answer, and my answer there is going to be that I have 25.8 moles of NH3. However, what you do need to remember is that your moles and your moles of H3PO4 have canceled out, but your kilo didn't, which means that your kilo here needs to continue. I have to get my volume of ammonia. So on the bottom, if I want to get to volume of ammonia, that means I'm going to have to put liters on the top and moles of ammonia on the bottom, which means I have 14.8 moles in every 1 liter. On the top, I'm going to have to set this up equal to my concentration, which is 14.8 moles in every 1 liter, and then I can put X liters on the left-hand side. In either case, the bottom of the top, I'm going to get an answer of 1.74 kiloliters of ammonia. The last example here again is a solution stoichiometry example. And this example gave us the volume and the concentration of one of our solutions. And what it's asking for is the concentration of the second solution. So as per usual, our first step is going to be finding the moles of what we know. So on the bottom here, I'm doing unit analysis, and my liters will cancel out, which means I'm going to have millimoles of KOH. On the top here, I am going to find that I'm doing 15.9 multiplied by 0.15, which is going to give me an answer of 2.385 moles. The same as on the bottom, we are going to have to keep the milli because we had a milliliter. If you don't want to do this, you can always change it into liters if you want before you start your math portion. Whoops, this should be KOH. I'm now going to use my mole ratio to get the moles of sulfuric acid. So on the top, I have to put my sulfuric acid because that's what I'm looking for. On the bottom, I have my moles of potassium hydroxide, which means that if I do 2.385 divided by 2, I'm going to get 1.1925 millimoles of H2SO4. And on the bottom, again, my moles will cancel out my moles, and my KOH will cancel out my KOH, which means the same thing. I have millimoles of H2SO4. Next step is I have to find my question mark. My question mark, I know I want my concentration to be in moles per liter. So in order to put my liters on the bottom, I have to put my 10 milliliters on the bottom. On the top here, I have 1.1425 millimoles of H2SO4, and I know that I have 10 milliliters. And what will happen is I do the math here, my milli and my milli will cancel out, and I have moles per liter. And I get my answer to be 0.119 moles per liter of sulfuric acid. And what I just realized down here at the bottom, 1 liter and 0.15 moles, so that I get the same answer. 15.9 times 0.15 divided by 1 divided by 2 divided by 10 multiplied by 1 multiplied by 1 is going to get me the answer of 0.119 moles per liter, the same.